Okay, class, let me share my screen on the PowerPoint on the topic that I will be sharing with you today. So, do you see my screen, class?
Yes, ma'am.
Okay, so it's about homogeneous differential equations, still under the group of first order differential equations. So let me just minimize this one. Okay, so now let's go to each of the slides in here. So before we get to learn to solve a first order differential equation, which is said to be homogeneous in the first place, we need to know what a homogeneous function is. Now, a homogeneous function has something to do, or the concept of the homogeneous function has something to do with the degree of each of the terms in that particular function. So let me start with this particular slide. So let's say you're given a function of x and y. So an expression that has variables x and y, and it is said to be homogeneous of degree n. So if it is of degree n, then there exists a constant n, and being a positive whole number, such that for every quantity r, which could be a variable or a constant, if we replace the variable x and y by the product of x and y with r, that particular variable which you have said, the original function is maintained, or its identity or its original form is, shall I say, maintained, and you have simply factored out r raised to a particular exponent, which is this particular constant n. Now, it's like in this particular example that you are seeing here, a very simple example, you're given a polynomial, a second degree polynomial. Why am I saying it's second degree? Because the terms, or each of the terms in this particular polynomial, is of second degree. Why do I say second degree? Because the exponent of the variable, or the sum of the exponents of the variables, if there are more than one variable, are in this particular example the same with value equal to 2. So this is 2. Your x and y here is said to be raised to 1, so the sum would be 2, and your y here is raised to 2. So each of the terms is of degree 2, or of power 2. So we say this particular polynomial is homogeneous of degree 2, or say homogeneous of second degree. So it's homogeneous in the sense that whatever is the exponent, or the sum of the exponents or powers to which the variables in your particular term are raised to, are the same. If they're not the same, then that particular expression, let's say, for example, this particular expression will not be homogeneous because the degree of the terms are not the same or equal. Now, if there's a question, would that particular variable miss, which we will multiply to our variables in our function, be really r? It could be any letter that you want. Later on, you can simply have it factored out. So you see it here. You can factor out the r squared, and that tells you already of the degree of your particular function. Why? Because your original function x squared plus 2xy plus y squared is still the same. So the identity is still preserved, and you have factored out r squared in the process. Now, if you have already factored out a common exponent of the r, and the original function is not preserved, let's say in here, you have x squared plus 2xy plus y squared. In here, after factoring out r squared, you still have an r in the middle term. Then we say that this function is non-homogeneous. If the function is non-homogeneous, you cannot solve your particular differential equation using the technique that I will be discussing in a few minutes. So it has to be first established that your functions, the functions that appear in your differential equations is homogeneous. Now, another example here is for this particular function, still of the variable x and y. Even if I will not change my x and y to rx and ry, because that's what is stated here, I can right away tell that this one is fifth degree. And this one is also fifth degree. Since both terms have the same degree, automatically this function is said to be a homogeneous function of fifth degree. Okay, if this is fifth degree and this one is fourth degree, the function is non-homogeneous. So they should have the same degree. So polynomials are homogeneous if all terms are of the same degree. So that's what we're going to check before we solve our differential equation, which is said to be first order. That is if we want to test whether it's homogeneous or not. Okay. Now, the first order differential equation in this form, in which you have the differentials of x and y, which have coefficients having variables x and y. So these are now our functions, is equal to 0. And this particular form of your first order differential equation is said to be homogeneous if and only if M and N are both homogeneous, so they have to be both homogeneous, and another one, they are of the same degree. What does this mean? Even if a particular function here or coefficient is homogeneous, but its degree is not the same as the other function here, your DE is not to be considered as a homogeneous first order DE. You don't solve it using the techniques that I will be giving in a little while. So the requirement should be both functions that appear in the differentials in your differential equation should be homogeneous and they should have the same degree. So I have placed in here another example. Let's say you're given this particular differential equation, the square root of x squared plus y, all multiplied to the differential of x plus x dy equal to 0. Before you even try to solve this using the homogeneous differential equation technique, check first whether M is homogeneous and N is homogeneous. So M is the coefficient of the differential of X and N is the coefficient of the differential of Y. So let's do that. Since this is second degree, but it's under a radical sign, the square root sign, then this x squared and y squared could be viewed to be also raised to the power 1/2. And as such, if you're going to multiply x and y by a particular variable, let's say r, then this will be r squared x squared, and this would be r squared y squared, and this x here would be ry. What will happen is you can factor out the r squared under the square root sign. And if you perform the square root, that would be r square root of x squared plus y squared. And this r here and the r, which you have already performed the square root of, could be factored out. So you can see now that the original identity of the m, which is this expression, is preserved. And r, the variable that you have multiplied your, or the letter that you have multiplied your variables, is now factored out raised to 1. So we say your m is homogeneous of degree 1. You do the same for the n, but good in this case because your n is simply an x. So if you're going to change it to rx, then you can see right away that it's homogeneous or of degree 1. Now, class, you need not really show this particular process when you solve your particular differential equation later on, because there are students who can right away tell whether the expression is homogeneous even if they don't perform this particular process. Likewise, you are not required to show this one. As long as you are correct when you assess that your expression of m and n are homogeneous, you need not show this one. The only problem, class, is this. If you have solved a differential equation which is not homogeneous, using the homogeneous technique, you cannot really arrive at the correct answer, or you cannot actually finish your differential equation. So then I suggest that if you can do this, so much the better, so you can see really that it is homogeneous. If not, just make sure that you are really that shall I say proficient already, or you are a master in just looking at it and then you know that it's already homogeneous. Okay, now So since we are able to tell whether our differential equation, first order, that is homogeneous, then we are now ready to learn how to find its solution. So finding the solution of a homogeneous differential equation is a two-part solution. You have to first establish its homogeneity. That was the previous slide that I have mentioned. And second, then that's the time that you're going to apply the solution. And when we speak of the solution class, there are actually two options available for you to use in determining the solution of a predetermined or established homogeneous differential equation. So let me explain the two methods using the five-step rule. The first thing that you're going to do, of course, is establish first that your DE is homogeneous. Then you can either use any of these two options, which would lead you to the solution of your homogeneous DE. The first thing that you will do is you set an expression v equal to y over x, or whatever are your variables there. Let's say, for example, your variables are r and s, then you change this y and x to r and s. Now, would this really be a v, miss, this letter that is equal to my variables appearing in my DE? It depends on you, but I suggest it has to be a v because our books and other books are using v. So you set up this particular equation. B is equal to y over x. Okay? Now, when do you set up this particular y is equal to v, v is equal to y over x? You see this note here that I have written. If your m of x and y is simpler in form, meaning the coefficient of the differential of x is simpler, you use the second option, and that is x should be equal to vy. Otherwise, if n of x and y, the coefficient of your dy is simpler, use y equal to vx. And this is the first option that I have mentioned. Simpler in form. So ang namin di klaseng simpler is simpler in form. So if m of x and y is simpler, this is your option, option 2. If n of x and y is simpler, use the first option. So let's say you have used this particular option. You need to express all the y's that appear in your differential equation in terms of x. So you could see in here that if I will get an expression in terms of y, in terms of x from this expression, cross multiplying x on the v on the left side will give me y equal to vx, right? So meaning everything, all the y's in your original DE should be replaced by vx rather. You change all the y's. Now, since you change all the y's in your DE to vx expression, that includes the y also that appears in that derivative itself. So meaning in your dy dx, the y here, let me annotate so you will see. So the y that you are seeing here should also be changed to vx. So if your dy dx now, if we change your y to vx, you perform differentiation here in the numerator using product rule. That is first term times the derivative of the second plus the second term times the derivative of the first. Then divide both the terms by dx because the d of vx here, the product of v and x, is divided by dx. In the process, you get to cancel this one. So you have actually now, in your original differential equation, replace dy dx by v plus x dv dx. So that's why we're using product rule of differentiation here. So again, set this equation. Then from this equation, get an expression of y in terms of x. And all of this will be the expression that will replace y in your original DE. So correspondingly, all y in the equation should be changed as well. So tanan nga y nga ga-appear sa DE mo, islan mo sang vx. And then the dy dx derivative should be changed to v. plus x dv dx. After integration, when you're done already with the integration process, replace all the v in the solution of the differential by y over x. Since v is not the original variable that you have, but rather y over x, in your answer later on, all the y over x expression should be changed, or all the v rather should be changed to y over x. Now, actually, option 2 is just an offshoot of this one. So you change the variable x to vy, and as such, the differential of x, you see this x here, in the differential of x, you change that to d vy. Then you are to use product rule. So that would be first term times the derivative of the second plus second times the derivative of the first. So your dx now is replaced by v dy plus y dv, still using product rule. Then replace dx in the given differential equation by the dx expression that you have in here. Correspondingly, all x in the equation should be changed as well. After integration, replace all the v, kana naman yung v nga ga-appear sa inyong answer, in the solution by the expression x over y. So all the v's that appear in the final solution should be changed to x over y. Okay, now this 5-step rule for the two options will now be illustrated using the following examples. Okay, I think it would be clearer if there will be examples to illustrate this particular 5-step rule. Okay, let me go to the next slide. Okay, so let's say, for example, you're given dy dx being equal to x squared plus y squared over xy. Okay, if you look at it, class, like mentally looking at it, if you transfer this xy in here and you transfer the differential of x in here, all by the process of cross multiplication, this coefficient of your dy is second degree, right? And then the coefficient of your differential of x, if it's already transferred here, are all also second degree. This is second degree. This is second degree. Since the coefficients of dy and dx are all second degree, homogeneous that is, then your differential equation is homogeneous. So you could see there is no shall I say, testing anymore. It's all done by the eye. So inspection, it's by inspection that we know that our given differential equation is homogeneous. Okay, so then, since we have established that it is homogeneous, then you try to check. So if you cross multiply xy here, and you cross multiply dx here, which of the two differentials will be as a comparison simpler compared to the other? So ining xy bala mas simple kumpara sa x squared plus y squared. I think you will agree with me that it is simple. So it is suggested that since your dy has a simpler coefficient, then your substitution equation should be, as I suggested here, if your n of x and y is simpler, use y equal to vx. And then this n of x and y, actually in our form, your n of x and y in our form is actually on the differential of y. That's a suggestion, class. If you intend to use the other option because you feel like you're comfortable with this particular option, it's okay. But normally, this is how it is a process. So para hapos. Okay, so in this case, in this particular problem, what was done first is, in the rational expression that is provided, the xy in the denominator was distributed. So you could see xy was used as a divisor for this one, and this was also divided by xy. In the process, using your algebra, the numerator is left with an x, the denominator is left with a y. Why is that? Because we get one x in here. So this is only one now. In here, same thing. We get the y in the denominator and this becomes 1. So now you have an expression which is x over y plus y over x. So if we get the reciprocal of the first term in here, that would be y over x raised to negative 1 plus y over x. Now, why do that? So that since you already have y over x here, they will be both uniform as y over x. Because we know that if this is written as a denominator, this one, because of the exponent of the negative 1, it would look like this, the x over y. So now you have y over x. So what is y over x? We know that y over x class is the v. Okay, it's the v. Your y over x is the v based on option. What option is this? Option 1. So transfer mo na di siya, ho, v na siya. So we start with this particular equation now. We copy. And this is the corresponding simplified form. The simplified form of this is this one already. This is the simplified form. So we copy it. So you have dy dx and copy this one in here. Then we substitute this one. Okay, y is equal to vx and dy dx will be replaced by v plus x dv dx. Question, Miss di naghalin siya sa option 1. Okay, ang option 1 naging gamit. So we replace dy, this dy by v plus x dv dx. You replace y over x by v because if you transfer the x in here, that would be. So this is v raised to negative 1 because this is negative 1 and this is v. Now you see there's a v here and there's a v here, so they will both cancel each other, leaving you with x dv dx and this one, b raised to negative 1. If you look intently, class, look at it intently. If this is written, the v raised to negative 1 as 1 over v, your differential equation is actually separable. Transfer the v here and transfer dx and x underneath on the right side. That's what I'm going to show to you on the next slide. So separable ni siya. From a homogeneous differential equation, it was made separable. So I will clear all my markings and we'll go to the next slide. So in the process, you have now b dv equal to 1 over x dx. That's our original expression here. This one. This v is 1 over v. So pag silo mo sang v dire sa babaw, it would be multiplied to dv. This dx will be divided by x. So that's the thing that you are seeing here being integrated already. Okay, so they're being integrated because anyway, we already separated the variables and grouped it together with the differential that has the same variable to it. When we do integration, excuse me, this would be power rule. This is the equivalent expression of this using power rule. And by power rule, the right side becomes ln of x. Don't forget the c because you don't have any limits in your integrals here. So since you have a c class, it's always suggested, class, that when you have a c, it should be an ln also. You can keep it as an ln of c or an ln of another constant if you want. So you have ln of k. Why, Miss? You may ask nga, Miss, si LN, good. Because in our textbook class, elementary differential equations by Bidient, Rainville, and Bidient, basta gani ang answer mo pag-integrate mo may LN, ang integral constant sina or ang arbitrary constant sina LN man na iya form. Why make it that way? So that it would be easier to simplify. Why am I emphasizing this? Because maybe at times you may wonder why you can't find the solution in the choices. It's because probably your answer has an ln and the arbitrary constant of integration was also represented in the form of an ln. So i-ln taman siya para ma-combine sila nga dua. Because if this is plus, from what you have learned in your differential calculus, property of an ln is if the two are being added, you can have it represented as one ln in which the two arguments, these two x and k are the arguments are being multiplied. So we write it that way. So in the other side, you have b squared over 2. We keep it because we can't do anything about it. If you transfer the 2 on the right side and simplify the left side by taking the square of this entire expression, you will have v equal to plus minus the square root of 2 ln of kx. If you recall our topic on explicit solution, this one is explicit. Why I say explicit? Because you are left with one variable on the left side. Okay, so it's explicit. Whereas if you have settled with this kind of answer class, this is also correct, by the way. There's nothing wrong with this. But nonetheless, if you don't see this in the solution, simplify using these particular steps here. That way you will have an explicit solution. Again, in the 5-step rule, if you have already arrived at the answer class, you don't have v in the original DE. So you have to return the v expression to what it was representing before. So your v is equal to y over x. Coming from the fact that in our option 1, this came from the fact that in our option 1, you have y equal to vx. So then your v is equal to y over x, as you can see here. So this v should be changed to that expression. So y over x. And look at this. If you have explicitly written your solution after you have done back substitution, we call it back substitution because the variable v was already changed into the original representation. When you do back substitution class, your answer is even easier to simplify because now it's explicitly written in the form y equal to plus minus x times the square root of 2 ln of kx. So you cross multiplied x here. So this is your answer now. Don't make that grave mistake of placing x here. No, x is multiplied to this expression, which can either take a plus or minus sign. So it should be multiplication. If you write x before, that would be interpreted as x plus minus the square root of 2 ln of kx, and that would be wrong. Okay? The process of finding the solution of the homogeneous DE is, if I may say, class, it is one of the longest, or if not the longest process in all types of first order differential equations. Really takes patience for us to finish the solution of a homogeneous differential equation. Why? Because of the process of substituting this expression to the original variables that we have in our DE. Okay, before I go to the next example, do you have any questions so far? Anyway, I will share to you the link later for this recorded discussion. So question? None. So I will proceed, class, huh?
Miss, mangkat lang ako, Miss.
Yes.
Kung ang C, Miss, hindi mo pag-change sa ln of k, bali mas square root ka, Miss, ln of x plus c.
Ha. So meaning ang gwa sinidere, let me take. So this one, amo ni siya be, ini siya could be the square root of ln of x plus c. So the ring apart.
Okay, Miss.
And then you transfer the 2 here and then get the square root.
Okay, Miss, thank you.
Okay. Or this could be not here, but rather dire na siya gali class. So dire na siya apart. Kaya dire wala pa siya ka square root. So this expression now, you will have times 2. So this should be 2. ln of x plus c. Okay. Some more questions? Okay, we go to the next example. I think we'll be ending here. I have 2 examples here. You have x squared plus 2y squared multiplied to the differential of x being equal to xy dy. By the way, class, if you see one differential separated from another by an equal sign, there's no need for you to transfer it on the left. That way you will have an equal 0 here on the right. No need for that. Just simply check whether If you want to test for homogeneity, the degree of the terms in the functions that are being multiplied to your differentials are the same. So in this case, this is second degree, this is second degree, this is second degree. All second degree. So your DE is homogeneous. Now, if you look at this particular expression, again, look at this particular DE, the coefficient of dy is actually simpler than the coefficient of dx. But look at the substitution that was used. So it really depends on the user on what particular substitution you will be using. Supposed to be if it's the differential of y being simpler in coefficient to the differential of x, the suggested substitution should have been y equal to bx. But in this case, it's the other way around. So it depends on you as long as you need to substitute a particular expression to your variables present in your original DE. Actually, this one is v equal to x over y in this case, or x is equal to vy. But this is option 2, if you recall. Dapat option 1, no? Based on suggestion, but it's okay if you use option 2. If you find it difficult later as you are solving to simplify your answer, then you may opt to switch option. There's nothing wrong with changing your shall I say, the route to the final answer when you realize that it's going to be difficult to simplify. Okay, so if you're going to use this particular substitution, I call this a substitution equation for x and for dx, your original DE would look something like this. So your x will be vy, so it's squared, so this 2 is squared, and your 2y squared is copied. Your dx is v dy plus y dv. And in here, you have vy for the x, and then another y, and then you have dx. The rest is your algebra. So you need to expand based on this one being multiplied to this. So the resulting expression is v cubed y squared dy. And you have 2y squared v dy if this is distributed to these two. And you have v squared y cubed dv and 2y cubed dv. And then this one here on the right was transferred here on the left side. So you have vy squared dy. The rest, again, is still algebra because you need to group the expressions which have the same differentials. Let me annotate. So when I say expressions which have the same differential, this first term, you group with the second term dy and this one. So there should be 3 terms which you need to group together. So you have these two having y squared, so it's already factored here, multiplying it to the expression b cubed plus y squared. This one, by the way, is the y squared plus b. Wait. 2y squared b. Okay, so you have a positive 2y squared b minus by squared. So that would be y squared b na lang. So these two were combined because you have by squared here and you have by squared here. This being positive, this one is negative. So that would be just by squared. And the y squared was factored out. Then the next is you group the dv's. Sorry naman ang dv. So you have the dv's. So the dv's will be grouped together with the y cube. So this one has the y cube. So this is b squared y cube, and this one has the 2. Okay. Now you have since this is y squared and this is y cube, you can actually cancel this one from here by division. This is left with simply y. So it's raised to 1. So you can see now that you have, excuse me, b cubed plus b dy, because I've canceled already the y squared here. And for the second term, you have y squared plus 2 quantity, b squared plus 2, and then you have y dv. If you look intently in this expression class at this point, you will see that it's separable. Why is it separable? Anybody who can tell why is it separable? If you divide the entire expression by v squared plus by y and v cubed plus b expression, the y is transferred here on the dy, and the v cubed plus b is transferred here on the v squared plus 2dv. So there's a need for you to divide the entire expression by, you need to get rid of this here because it's differential of y, so you divide by b cubed plus b. Whatever you need to get rid in a particular term, you use that as a, you eliminate it by division. In here, you need to eliminate the y because your differential is dv, so you divide by y. This divisor class is true for the entire equation, so the result would be something like this. This one would yield the dy over y, and this one would yield a b squared dv over v cubed plus b, and then you have a 2 dv over v cubed plus b. What was done is the v cubed plus b was distributed to the two terms in the numerator. Now here you can factor out the v, so you have v times the quantity v squared plus 1. And if you use v equal to the tangent of theta, dv will be equal to the second squared of theta d theta. You just simply differentiate this equation. So now you change the dv to second squared theta d theta. You change the v to tangent of theta. And you change the v squared plus 1 to the v being tangent squared because v is tangent plus 1. Now, this would be equal to, so if we simplified, this one is 1 over cosine squared theta, and this is sine over cosine. The simplified form class of this answer is actually this. Why, miss? Sa inyo nga trigonometry, tangent squared theta plus 1 is secant squared. So that's left with a 1 over tangent, tangent being sine over cosine, so you have this. So the integral of cosine theta d theta over sine theta. You have the answer to be an ln because if this is your u, this is your u, your numerator is your du. So it's an ln of sine theta. So your answer then is ln y for this. So we answered this one, huh? So ln of y. For this one, class, you have this one will also be, wait, why is it an ln of v squared? It's not indicated here. B squared plus 1. Okay, there's a need for me to simplify this. If you will factor out the v in here, it will cancel one of the v's here. So you will have v dv. And your denominator, if you have already factored out the v, will be v squared plus 1. If you set this as the u, the du will be here in the numerator. This is your du, provided that you place a 2 here and you place a 1/2. So that's the reason why you have a 1/2 ln of v squared plus 1. For this, your ln of y is for this. And this one is our answer for this integral. So 2 ln of v over the square root of 1 plus v squared. Now, our answer here is actually sine theta, right? And you just finished your integral calculus. This is actually trigonometric substitution, right? So if you have a right triangle, so this is a review of your integral calculus. This is theta. The tangent, which is b understood to be over 1, is v opposite over the adjacent. Your hypotenuse is then b squared plus 1. And since we answered here an ln of the sine of theta, that's equivalent to, I'll place it here, ln. Ano ang sine tabla? Opposite over the hypotenuse. So it's a v over the square root of b squared plus 1. Now, Miss nga may 2 dira. Did you see this one? It's a property of an ln that whenever you have a constant written before it, it could be written as an exponent of this one. So now you can see that the 2 that is written before here was transferred as a form of exponent for this entire argument of the ln. So ang nagwa ka sa muniho ln of, ini siya ang 2 will be exponent of the 2. So this is b squared. If a square root is raised to 2, that will get rid of the square root. So that would be b squared plus 1. And then look, the c was represented as an ln of c. Do you get it? Now, if your terms here, tanan mga terms are all in the form of the ln, if you will simplify by making all these arguments of your ln as products and make the entire equation as the exponent of the e, this will be your answer. For this original, this is your original integral. Okay? So that's how calculus beautifully gives you the solution to your DE. If not for calculus, you will not finish the solution of this DE, even if you know how to solve a homogeneous differential equation. Now, the rest of the part in here, class, the rest of the part in here is by substituting the V. What is V in the first place? This is not our final answer because we have a V. Our V, based on our substitution, our V, I'll write it here, our V is equal to X over Y. Okay, V is X over Y. So all these V's here, which you will need to square, will be changed to X over Y. I leave to you as your part the understanding of this final answer. So actually, this is the final answer to our homogeneous differential equation, which is this one. So we resubstitute X over Y to V, we simplify, and this is our answer. Now, you can also have another option, the other option, this one, and look, if you went with the suggestion that whenever the coefficient of Y is simpler, your substitution will be Y equal to Vx. In here, we change V to U. The process is shorter. Okay, the process is shorter compared to this one. So actually, it really depends on what option you will use. You may just, as you go along class practicing, you will realize that one option is best compared to the others, because there's just 2 options in here. So this particular part in here is using the first option. This one used the second option. Look at the way it made you review your integral calculus. But I think, as I use the word, it beautifully applied what you learned in integral calculus. If not for integral calculus, you will not finish this particular differential equation. Okay? Anyway, this is recorded, so you can go back to the discussion in this part if you find it now very fast when I'm discussing it, and I leave this to you to understand. But anyway, the procedure here is the same 5-step procedure as indicated in the first option or in the second option that was used. However, class, of course, the integral process will be different because your resulting expression, they are not the same when you use a different substitution equation. Okay, let me clear the markings here. And let me check what I have in the next slide. Okay, I don't have anything in the next slide anymore. So I used 4 minutes of your time. I hope you don't have any class. But nonetheless, my questions there. Do you have any questions here? You can go back to our you can go back to the recording later, which I will be posting. No more questions. I will stop sharing. Okay, class. So that's homogeneous DE. it is my practice in the even in not COVID times that if I have covered already at least 3 types or 3 techniques, that's the time that I give sample problems that are already solved for you to read. That way I can make you do your own practice. Okay, you do your own practice, you find the available resources in the internet, or if you have a soft copy of the book, do your own thing. As I say, you always practice because that's the only way that you're going to be good at what you are doing. Okay, so this will be our last meeting for the week. We will see each other again on Monday next week for a new topic, and that would be exact differential equations. Okay, if you have any questions, don't hesitate to message me in Canvas or at Messenger. You can leave a message for me in Messenger. So bye for now, class, because I already eat up your time. Thank you so much. I'll see you next week.
Thank you,
Thank you,
Miss.
Miss.
Thank you,
Okay,
Miss.
Miss.
Thank you, Miss.
Thank you,
bye-bye.
Miss.
Thank you, Miss.
Bye-bye.
Thank you, Miss.
Welcome.